All right. Hello, everyone. As previously mentioned, we are a group of undergraduate students from WPI located in Worcester, Massachusetts, and we worked with Rehub addressing glass waste in Venice. I'm Thomas Boyle.
I'm Joseph Cardarelli.
I'm Lexi Joseph.
And I'm Matt Winchell.
Now, glass waste is a worldwide problem. When we look at glass production as a whole, Europe is the world's largest glass producer, with roughly 1/3 of the market share being produced here in Europe. When we look at glass waste produced in each country, Europe produces over 8 million metric tons per year, and Italy contributes to 235,000 metric tons of that 8 million.
Rehub is addressing this problem. They're a startup company based in Murano, created by Matteo Silverio, and their mission is to merge tradition and handcraft with innovation and design, striving for a zero-waste society. And they've won many awards for their work, including some from MIT DesignX, the Corning Museum of Glass, and the Wadsworth Atheneum. They have a very unique process to upcycle glass that is formerly non-recyclable. They take that glass waste and they grind it down into a powder, and then they mix it with their proprietary binding agent to create the paste that you can see on screen here. They can then use this paste in manufacturing processes such as 3D printing, injection molding, and rolling to create brand new products like the one you can see on screen. But Rehub wants to scale up. Currently, they're only grinding 200 kilograms of glass waste per week. Their goal is to process 500 kilograms of glass waste per hour, as that is the amount that an industrial glass producer can create in that amount of time.
This brings us to our team's mission, which is to assist Rehub in industrializing the process of turning glass waste into a reusable paste in a sustainable and scalable way. Rehub has created a unique 5-step process to achieve this, beginning first with the glass input. Glass is inputted into the machine, where it is then ground down through 2 cycles into 2 consistencies of glass powder, a coarse powder and a fine powder. These are then transferred over to the mixing stage, where the 2 powders are mixed in proper ratios with certain binding agents, which then produce the proprietary paste. The proprietary paste is then brought to the paste output, where it is compressed of excess air and able to be manually collected for manufacturing use.
If we visually go over the process again, we start with the overall machine package. We first start with the glass input stage. So the glass gets input into the grinder. The grinder then grinds the glass into 2 different consistencies that, when combined in different ratios, can create a unique appearance in the product. It then can be divided up into their own storage containers. It then gets transferred into the mixer. The mixer mixes it with proprietary chemicals and then gets compressed and output from the machine. So we have some overall machine requirements that we need to meet. The first requirement is a 500 kilogram per hour throughput. The next requirement is to package the machine in a standard shipping container. The next requirement is have little to no human interaction. And then we need to be able to control the glass particle ratios to create this unique appearance. So if we look at some images, the image to the left shows some coarse glass powder, and then the image to the right shows some fine glass powder. When you combine these in different ratios, you can create a unique product shown here and what Lexi just showed. So if we go into the specifics of the machine, again, we're starting with the glass input stage. Firstly, it needs to support glass waste as large as 20 centimeters by 30 centimeters, and then we needed to decide between a manual input versus an automatic input. So the team decided on a hopper as the most appropriate option. It can, in fact, support the glass waste input and throughput, and you can ask for the specifications from the manufacturer alongside the grinder. The next phase is the grinder itself. So the grinder needs to be able to grind glass at 500 kilograms per hour, and it needs to grind that glass anywhere between 0.1 millimeters and 1 to 10 millimeters. And lastly, it needs to be below $30,000 USD. So the team decided on the Chima PD1 grinder. It can, in fact, process glass at 500 kilograms per hour, and it can grind that anywhere between 0.1 to 5 millimeters. It can do 2 different cycle times to acquire those 2 different particle sizes, as I mentioned. And these are the dimensions shown here. The 1,500 millimeter dimension includes Chima's hopper, as I mentioned previously. And the overall cost is €27,000.
The next thing we needed to develop was the transfer system. So it needed to separate the two particle sizes, the fine and the coarse glass, into their own storage systems. Each storage container needed to have enough overhead storage between the grinder and the mixer to allow for downtime in either process. And it needed to be able to support that 500 kilogram per hour throughput that the grinder is producing. It also needed a very controllable output into the mixer to really fine-tune the ratios of the fine to coarse glass to get a controllable look of the final paste product. This is the design that we came up with. It uses a simple diverter shown in gold on screen that separates the material sizes by blocking off the left or the right side, sorting the proper material into their storage containers, which you can see in pink. Those storage containers hold roughly twice the capacity of the mixer, allowing for plenty of overhead between the two processes. Shown in purple here is the transfer system that we designed based off of the Archimedes screw to transfer the material into the mixer. It supports very large throughputs, meeting the 500 kilogram per hour throughput of the mixer, or of the grinder, and it has a very controllable transfer rate. You can determine exactly how much material is input into the mixer by controlling the number of rotations that the screw makes.
In the second to last step in our modular process, the mixing stage, we were tasked with identifying a mixer that is able to match the grinder output. This mixer also needed to be able to have a binder and a colorant input to control the final paste consistency, as well as sensors that can monitor when the final paste is completed. We also needed some way that the mixing process could move the final paste into the output process. We decided that the best way to do this was to design our own paddle mixer using different aspects from various industrial mixers that we identified. So as shown in red, that is our design. It is able to mix 100 kilograms of paste at a time. It has 3 different sensors, a moisture sensor, a torque sensor, and a pressure sensor to monitor the final paste, and it has input for the binding agent as well as different colorants.
The final section of the machine that we designed was the paste output, which had various requirements that we had to include. The first being maintaining a consistent paste quality throughout the process. It had to match the actual mixer throughput, as well as include a compressing mechanism to reduce excess air out of the paste. We designed different aspects of a pug mill into our own design, which allows excess air to be compressed out of a material. We use this aspect to compress the paste, and then the brown screw showed on screen is what drives the paste through an increasingly small diameter to compress the paste where it can be manually collected at the end of the machine for manufacturing processes.
This is our final preliminary design model of the machine. As you can see, the dimensions are shown here, and then we have a 6-foot tall worker for scale. So if the machine did, in fact, meet the 500 kilogram per hour throughput, it can in fact control these different particle sizes to create this unique paste appearance and therefore a unique product appearance. And we recommend that the sponsor uses this as a preliminary design to inform his future designs. And lastly, we can fit roughly 4 machines in a standard shipping container. We chose a shipping container because they're easy to transport, and as shown here, you can ship them in bulk, which will be cheaper.
The team also developed a simple mock user interface to control the machine. On screen, you can see that it has controls for both the grinder and mixer, as well as sliders to control the ratios of the fine to coarse powder, as well as controlling the ratio of the binder and the glass itself. There are also sliders to control the amount of colorants added to the mixer. As well, in the bottom right corner, you can see an emergency stop button, which is always visible on screen in case anything happens. Shown here is an example of what the screen might look like with some of the sliders configured, as well as some of the switches flipped. In the top right of the screen, you can see a little white button. Tapping that or clicking on that will open up a side menu where you can see sensor information, allowing you to easily determine when the paste is finally finished. As well, you can see a model of the machine, which in this example here, you can see turns green if the machine is running to denote how it's working.
Now that we have discussed how we will produce the paste, the team also researched 4 potential paste applications, which include pieces in the art industry, different fashion items, tiles, and countertops. The first industry that we researched was the art industry. Early Rehub products included 3D printed baskets, wire racks, bowls, vases, and other various decor items. As shown in the pictures, these processes begin by the paste being 3D printed and then heated to shape the desired bowl at the bottom of the screen. These products are great for marketing and promotion and is what Rehub currently uses the paste for in its early stage. However, the team notes that art material sales can fluctuate, and marketing and distributing the paste to artists could be difficult. Therefore, we suggest it is not the most reliable market to solely dedicate its paste to. The team also researched items in the fashion industry. It is a $341 billion industry worldwide. However, it is important to note that glass products contribute to at most 20% of this number. This is because gemstones and precious metals are already considered in the worldwide industry value. Ceramic, porcelain, and glass are the common materials used within this industry, as seen in the 3 pictures to the right of the screen. We researched the cost and manufacturing techniques of common jewelry and fashion materials, including glass rods, glass sheets, ceramic paste, and compared this to the Rehub paste. While the Rehub paste is slightly higher in the average cost per kilogram, it is important to note that the hidden costs compared to the other ones are much lower, as you can use 3D printing and injection molding with the Rehub paste, whereas the others require human labor to handcraft the materials. It is important to note that the amount of paste used for each unit would be rather low in this industry as you're making small products. Therefore, it creates a lower market demand compared to some of the other industries we researched. Therefore, we suggest that Rehub explore other opportunities where it could produce the paste products in bulk.
The next industry that we researched was the tiling industry. This is a $227 billion industry worldwide. And as you can see on the images to the right, these are some early examples of Rehub's products. We researched the average production cost, maintenance, and the manufacturing process for other popular tile materials, such as ceramic, porcelain, and 3 different types of glass: sintered, cast, and float glass. As you can see on the chart to the right, the cost for Rehub paste is very similar to other types of glass, as well as the manufacturing process. However, we did note that with the grout and adhesives that need to be used in the tiling process, there's a severe lack of upcycling for the Rehub paste application. In order for us to align with our sponsor's mission more, we decided that this was not the best for the Rehub paste in order for the Rehub paste to be upcycled in the future. The final industry that we researched was the countertop and tabletop industry. This industry is a $131 billion industry worldwide, and within this industry, recycled glass countertops are a steadily growing market. We researched similar common countertop materials, and we researched the cost per square feet for both the producer and the consumer, as well as the required maintenance and the manufacturing technique. As you can see, since the Rehub paste is made from recycled materials, the production cost is much lower than the rest of the materials, and the manufacturing process is very similar to quartz and stoneware. This led to our decision. Rehub paste production as well is estimated to decrease with higher demand, which makes the consumer cost lower. We decided that this makes countertops and tabletops the most viable market for the Rehub paste application. And as you can see on this image, Rehub is exploring this industry with smaller scale tabletops.
So let's take a look a little bit with the environmental impacts of what we've done. So each year in Murano, over 1,000 metric tons of glass waste are produced. However, with just one machine running for 40 hours per week, we can process that 1,000 metric tons of glass waste each year. So on that scale, just one machine can cover all of the glass waste in Murano every year. And if we expand just a bit further, with 235 machines, we can cover all of the glass waste produced in Italy every year. So with that, we are very hopeful that our work can have a great environmental impact on this glass waste issue. Thank you all very much for listening.
The team will be happy to answer any questions at this time, and we will also pass around some of the samples for everyone to see.
Anybody have any questions or comments before I pass the microphone to Matteo to hear what he thinks? Anybody else? Some of the other startups there in the crowd here? This is the kind of thing that students could do for your startup next year. Not necessarily an industrial thing, but. You guys have a question? Okay.
Thank you very much for the presentation. It was very inspiring as a solution. I think the owner, you run the company, isn't? So I want to ask, like, is it already in production and you have the machine ready, or?
Sorry if the echo. I love this place. I love this place. You have to read the book. But I have the machine, right? Well, not this one. Thanks, guy, by the way. Really thank you. We have now, I mean, the process is the same, okay? We are running the process using different machines. The limit today is that every step we perform, we need human labor, which is not a problem by itself, of course, but it's not safe, it's costly, and it takes time. That's why we basically set up this challenge to the students, say, okay, guys, can we do something automatic? And that's why basically today we cannot go higher than 200 kilo per week. It's a bit more, in fact, but more or less that is the average. Okay, with this machine, we can make way higher volume we can process. Sì. Since I have here, no, I will really thank the guys, the students, because they've been really constant. And I don't know how to say in English when you devoti alla causa. Dedicated. Okay. In Italy we say that you are, I mean, siete stati colti da grande forza e spirito di abnegazione, which is an old-fashioned way of saying that, but if some policeman, someone die while they're working, okay, and it's commemoration, they write spirito di abnegazione. It's the higher good thing they can say, okay. Luckily you are here. No, they are really good and they are constant. We have constant meetings till almost the end, because of me, not there. And they've been good interaction, which is, I mean, at the base of a good teamwork. And I'm just happy, and I would again to say thank you. They deserve a good grade. I mean.
I only have a question. If you calculate energy balance of this process, of this system.
So
Sorry, the question.
it's okay. We were looking into doing this, but it was a little hard to determine because a lot of stuff is still unknown about like the heating and stuff like that. So there was a little bit of like too much uncertainty in what we were able to calculate with the energy cost.
We made internally at the lab some researchers, and basically processing 1 kilo of glass with this process compared to, I mean, a normal glass manufacturing process, you can save up to 70% of the energy. Why? Because this is a process on demand, while usually a glass furnace needs gas 24/7, and also because we are using electricity and not gas.